I welcome you in today's session of physics. And in physics, we are discussing a topic rotation. This is your chapter number 10. As you can see here, center of mass. Clear? We had already covered out most of its topic in our lecture number 1. Now today, this is the lecture number 2, and we are going to discuss about center of mass of a uniform rod. Clear? You can see here, this is the topic we are going to discuss right now. So you can see here from this figure, this is a uniform rod of length AB, or you can say that small l is the length and m is the mass. Fine. So let its total mass small m is uniformly distributed over its entire length. Fine. Means the mass at every point is same. So the rod is positioned in such a way that its length is along x-axis. You can see here, this is the length is along x-axis, and one end of the rod is situated is at origin, and this is the origin of a rectangular coordinate system xy. Since a uniform rod can be imagined, this is the figure we are talking about. Uniform rod can be imagined to be a system of point masses placed continuously along a line. We are considering here the point masses are situated at this line, small m. Therefore, the method of integration is most appropriate method to locate the center of mass. So we are considering here an elemental length of the rod CD. You can see here we consider a small length CD, fine, which is of thickness how much, dx. Clear? So you can see here dx tending to 0 at a distance x from the origin x, means this distance is very very small. So as you know very well, mass per unit length is equals to how much, m by L. Therefore the mass of the elemental length CD of the rod is how much, you can, because the dm means the center of mass of this length is very very also small, so we can write this formula like dm is equals to m by L into by dx. Clear? Now you can see here, but x coordinate of the center of mass of a rigid body. So if we write the red x coordinate as we did in the above topics, so xcm is equals to how much, integration of xdm by dm. So the position of the center of mass of the rod along the x-axis, you can write it like this. And after solving all the expressions, we get here center of mass of x-axis is equals to how much, L by 2. So actually we can say that the center of mass of a uniform rod is located at its midpoint. This is the important one. Fine. As we discussed about the cone in our previous lecture, the center of mass of the cone is situated is h by 4, means total at the height of h by 4, which is 1/4 of its total height. Now here you can see the center of mass of a uniform rod is situated at half, means at its midpoint. Clear? Now we will move to the motion of center of mass. So let us consider a system of n particles whose masses m1, m2 up to mn and their position vector r1, r2 up to rn. So relative to a fixed origin and subjected to the external forces f1, f2 up to fn exerted by the surrounding, the position vector rcm at the center of the mass of this system is defined by this, where you know very well the capital M is the masses of all the particles of n particles. So differentiating it with respect to time, and finally we get, after solving the above expression, I am now going into the deep. You can see here, after solving out you will get this relation. Clear? Now what is am? Here you can see in this is written as m vector acm. So what is vector acm? Is the acceleration of the center of mass. Clear? A1 you can see is the acceleration of the particle m1, and so on. So now from Newton's second law, the external force F1 acting on the first particle is given by Newton's second law. I hope you are familiar with F equals to ma. So that from there we can write it like this, vector F1 is equals to m1 vector a1. Fine. So from the above expression, from this one we can write this equation like this, ma vector cm is equals to f1 vector plus f2 vector and up to fn vector. Or you can also write it like this, from this one, MACM is equals to F external force. So where F external force is the sum of the external forces acting on all the particles. Clear? Thus the product of total mass of the system of the particle and the acceleration of its center mass is equal to the sum of the external forces acting on the particles. So we can say that this means that the center of mass of a system of particles move as if the entire mass of the system were concentrated and all external forces were applied at it. Fine. So this results hold whether the system is rigid body with a particle in fixed position or a collection particle with internal motions. Now here you can see that is written in isolated system. So from the above equation, that is your equation number 2, you can see here from this equation what happened. F external force is equals to 0 means isolated system. I hope you are no variable which is not reacting with the outer space. Fine. So the external force is equals to how much in this situation is equals to 0. So if the force comes out to be 0, the acceleration is also 0. That is, you can say that the vector velocity of center of mass is the constant, or the vector sum of the external force is 0. That is, the velocity of the center of mass comes out to be constant. So this is the definition. You can see here what is written it. If the vector sum of the external forces acting on a system is 0, that is direct, the system is isolated, then the velocity of the center of mass of the system remains constant. So this is an important property of center of mass. Now here are some example of motion of center of mass. You can see here. First one, you can see the explosion of the bomb. Fine. These are the examples. So when a bomb placed at a point explodes, then its fragments fly in all the direction. However, the bomb explodes due to its internal energy and no external forces is present. Thus, the center of mass of all the fragments remain at the point where the bomb was placed. Fine. Now see the second one. What is radioactive decay? You can see from this relation or figure. Let us consider 92 uranium-238 nucleus moving with some velocity. So it decays by emitting an alpha particle. I hope you know very well alpha particle, 2He4, which is of positive in nature, and convert it into thorium nucleus, which is 90 thorium-234. Since no external force is present, so decay takes place due to its internal forces. All the process is going on due to its internal energy or forces from one molecule over the other. Now since no external forces present, so decay takes place due to internal forces. So the center of mass of 90 thorium-234 nucleus, an alpha particle denoted by C, that is continues to move in the same direction in which the decay 92 uranium-238 nucleus was moving. Fine. Now you can see here, this is the last one, explosion of projectile. I hope you familiar with the projectile motion. This is your first chapter of the book. So when an explosive projected at some distance or angle with a horizontal explodes at some point of the path, then the fragments fly in all directions. However, the center of mass of the fragments continue to move under the effect of gravity. Clear? So as the explosive was moving before collision, the position of the center of mass was indicated by, you can see here, C1, C2, C3, C4. This is the position of the center of masses. Fine. Now this is the last one of your momentum of conservation, an important topic. So read it properly. What we are going to discuss here. Let us consider a system of particles of masses m1, m2 and mn. Clear? Respectively, velocities, their velocities becomes v1, v2, v up to vn. So the total linear momentum of the system would be the vector sum of the momenta. Momenta is the plural form of momentum of the individual particle, and you know very well what is momentum. From the above definition we can write it, the sum of the momentum. So vector p is equals to p1 plus p2 up to pn if there is an n particle over there. So in place of p we can write it, I hope you know very well, p is equals to mv. This is your momentum. Clear? So that is the thing we had written here, m1 v1 vector plus m2 v2 vector up to mn vn vector. Now by the definition of the velocity of center of mass of a system, we can write it like this. Velocity, this is the we had already covered in our previous lectures. This is the relation between velocity and the mass of the system. Fine. So where m, capital M, is the total mass of the system, and we can write it like this, p is equals to m vector vcm. Clear? This is the relation between mass and the momentum. So we can say that the total linear momentum of a system of a particle is equal to the product of the total mass of the system and the velocity of its center of mass. Clear? You can see here, this is the definition, total definition. So this suggests that the momentum of the system is the same as if all the mass were concentrated at the center of mass moving with velocity how much? Vector vcm. So vcm is known as the system velocity. So if we differentiate the above expression, this one, clear? So if we differentiate it with respect to the time, you can see here dp by dt m dv over dt. So you will get here, you know very well, the change in velocity with respect to time is your acceleration. So this relation comes changes to m into acm, and this is also you are familiar with the Newton's second law, F is equals to ma, clear? So that is the thing written here, ma vector is equals to f external, that is the sum of all the external forces acting on the system. Fine. So by Newton's third law, the internal forces cancel in pair. Therefore, what happened? In place of ma vector, we can write it dp over dt is equals to f external force. I hope it is clear. Thus, the time rate of change of momentum of a system of particles is equal to the vector sum of all the external forces acting on the system. In that case, if external force is 0, then what happened? Then the ratio, this your differential of momentum, that is dp over dt, is also 0, and we can write it like this: vector p is equals to constant. Clear? So if momentum is constant, then the momentum of all the n particles comes out to be constant. So you can see here it is written that this is this definition: when the vector sum of the external forces acting on a system is 0, the total linear momentum of the system remains constant. This is important one, so kept in mind. This is the principle of conservation of linear momentum. Fine. Now this is a very small topic, just read it. What is the difference between center of mass and center of gravity? This is important one. So first one, you can see here, center of mass of a body is that point at which the entire mass of the body can be assumed to be concentrated. Clear? What is center of mass? A center of mass is that point where you considered the whole mass of the body is to be concentrated. So for describing the translatory motion of the body, while center of gravity of a body is that point at which the entire weight of the body can be assumed to be concentrated for describing its translatory motion. Clear? Now the second one, the mass of the body remains constant and it is independent of its position, while weight of the body depend on the acceleration due to gravity, which is depend on position of the body. So these are the differences between center of mass and center of gravity. These are both are the important one, so please remember it. So you can see here, this is the end of the chapter, students. We will meet in our next class with a new chapter. Till that, do study with students. Thank you class. Thank you very much.